The Great Pyramid alone required moving over 2 million multi-ton stone blocks. Ancient builders achieved this impossible task not just with architectural vision, but through revolutionary advances in quarrying. This is the hidden story of how innovations in cutting stone from the earth directly enabled the world's most iconic monuments. You will discover the precise technological leaps that transformed entire mountains into timeless masterpieces. How did workers in an Egyptian quarry manage to detach a perfect obelisk from solid bedrock? What simple machine allowed the Romans to industrialize their stone production? By the end, you will see every ancient wonder not as a finished structure, but as the final step in a much older, more dramatic story of extraction and ingenuity. What forgotten human effort do you think is still carved into the stone of our greatest landmarks? Monumental quarrying begins with a silent conversation between human ambition and the earth itself. It is not a matter of random digging but a precise and calculated craft. The first challenge was always finding the perfect stone. Ancient prospectors needed an almost intuitive sense of geology, searching for beds of rock that were not only beautiful but also structurally sound, free of hidden cracks or weaknesses that could shatter a dream centuries in the making. Once they found it, the real work started. How do you convince a mountain to give up a piece of itself and in a perfect shape, weighing hundreds of tons? This was a logistics puzzle on a colossal scale. Every block had to be conceived not just as part of a future wall or column, but as an object that could be physically freed, moved, and lifted. The quarry was a kind of open-air factory, the first and most critical phase of construction where the vision for a temple or tomb was literally rooted in the landscape. The techniques invented there, from shaping a block to transporting it, became the invisible foundation of every stone that followed. Without these unsung quarrying heroes, the architectural marvels we know would have remained forever trapped in the bedrock. This foundational shift in how stone was sourced set the stage for a revolution in ancient Egypt, where the quest for perfection led to one of history's most elegant and simple machines. That silent conversation with the earth began far earlier than the pyramids, in the misty landscapes of prehistoric Europe. Here, communities without metal tools or written language undertook their own monumental tasks. The iconic bluestones of Stonehenge, for instance, began their journey over 150 miles away in the Preseli Hills of Wales. How did they achieve such a feat? Their methods were a brilliant application of simple physics. Quarry workers would first locate natural fissures in the target rock. Then they would build fires directly against the stone surface. Once the rock was sufficiently heated, they would swiftly douse it with water. The resulting thermal shock, the rapid expansion and contraction, would create clean fractures, effectively convincing the stone to split itself. The final shaping was done with painstaking patience, using rounded stone mauls and sturdy antler picks to chip away at the stone, block by block. This was not the work of a centralized state, but of collective community will, likely driven by deep spiritual beliefs. These earliest quarriers proved that the human drive to extract and erect, to leave a permanent mark upon the world, is an ancient and powerful force. This primal ingenuity would soon be systematized, leading to a revolution in the sun-baked quarries of Egypt. In the sun-scorched quarries of Egypt, a profound shift was taking place. The monumental scale of pharaonic ambition demanded more than just community effort. It required a systematic and repeatable technology. The key breakthrough was not a single tool, but a powerful combination. Workers wielded heavy dolerite stone pounders, a type of igneous rock harder than limestone, to pound out channels and define the rough shape of a block. Then came the precision of hardened copper chisels. This two-step process turned brute force into controlled engineering. but the true elegance was in the final release. After carving deep channels around a block, workers would hammer dry wooden wedges into the grooves. Then they would pour water over the wood. As the wedges absorbed the moisture, they swelled with immense, irresistible force, cleanly and predictably popping the multi-ton block free from the living bedrock. This method was a quiet masterpiece of applied physics. It allowed for the extraction of the flawless white limestone from Tura that would sheath the Great Pyramid and the colossal rose-red granite obelisks from Aswan. This was no longer just quarrying, it was the birth of a stone industry. A single innovation in extraction directly enabled the iconic smooth slopes and towering monuments we recognize today. Yet, even this level of precision had its limits, especially when the material itself seemed to fight back. Granite is a stubborn material, a crystalline beast that fights back against the hammer. Yet in Aswan, Egyptian engineers chose to confront this challenge on the grandest scale imaginable. The unfinished obelisk, still lying in its bed of rose-red stone, is a masterclass in ambition frozen in time. It would have stretched to a height of nearly 130 feet and weighed an estimated 1,200 tons. To even begin such a project required flawless planning and immense courage. The evidence is still there, carved directly into the bedrock. Workers used heavy dolerite balls to pound out deep, narrow trenches, following the precise outline of the obelisk. This was a slow, thunderous process of pure percussion, a symphony of controlled destruction, but the true stroke of genius is visible underneath the partially freed monolith. Before they could even think of moving it, they had to support its impossible weight. The quarry workers carved a series of slots and inserted massive wooden beams, creating a supportive cradle that would hold the obelisk securely the moment it was fully released from the earth. This was engineering on the edge, a breathtaking calculation of force and counterforce. The project was ultimately abandoned, likely due to a catastrophic crack that appeared in the stone. Yet its failure is more instructive than any success. It shows us the absolute limits of Bronze Age technology, a testament to the human will to attempt the impossible, even when the mountain itself says no. This relentless pursuit of bigger and more perfect stone would soon be industrialized on an unprecedented scale by the Romans. Iron tools brought a new kind of conversation with stone, one of sharp, metallic precision rather than brute percussion. With durable iron chisels and picks, Greek and Roman quarry workers could carve into the hardest marbles and granites with a confidence their Bronze Age predecessors never knew. They could score deeper, define sharper angles, and refine surfaces right at the source. But the true revolution was not just in cutting the stone, it was in convincing it to move. The simple machines of the lever and the pulley transformed the quarry floor from a scene of immense strain into one of calculated mechanics. Picture a team of workers, not 1,000 strong, but perhaps a few dozen. They slide a long wooden beam under the edge of a multi-ton block. Placing a sturdy rock as a fulcrum, they apply their collective weight to the other end. With a groan of protesting wood, the impossible weight begins to pivot, rising inch by controlled inch. This was the practical application of a profound principle, the same one that led Archimedes to his famous boast about moving the world. The pulley system amplified this advantage, allowing teams to redirect force, lifting blocks vertically or pulling them horizontally with ropes. This mechanical advantage was a complete game changer. It dramatically reduced the risk of injury and block damage, while increasing the pace of extraction to an industrial level. The Romans did not just build with stone, they systematized its very birth, turning quarries across their empire into highly efficient production centers that could feed their endless appetite for temples, roads, and amphitheaters. This relentless drive for efficiency would soon push Roman engineering to its absolute limits. In a quarry so vast it became a landscape of its own. Roman logistics turned the chaos of raw stone into a predictable, flowing system. At quarries like Carrara in Italy and Mons Claudianus in Egypt, the work was no longer just a matter of extraction, it was a matter of state-run industry. These were not simple pits in the ground, but sprawling, organized complexes with dedicated living quarters for workers, administrative offices, and precise schedules governing the flow of material. The true stroke of genius, however, was carved directly into the ground. To solve the immense problem of moving multi-ton blocks from the quarry face to the loading ramps, Roman engineers cut parallel grooves into the solid rock floor, creating what were essentially rutways, the world's first railroads for stone. They would then place a heavy sledge atop wooden runners that perfectly matched these grooves. This simple but profound innovation drastically reduced friction. Instead of a sled fighting against every bump and pebble, it was now guided smoothly along its predetermined path. A team of oxen or a coordinated group of men could then pull loads that were previously unimaginable, moving blocks weighing 50 tons or more across incredibly difficult terrain. This was engineering brilliance applied to the problem of motion itself. The Quarry Railroad demonstrates that Roman power was built not just on architectural vision, but on an unparalleled mastery of logistics, transforming the monumental into a manageable, almost routine operation. This relentless drive for efficiency would eventually push them to reshape entire landscapes, creating quarries so vast they became permanent scars of human ambition. The thunderous silence of the abandoned imperial quarries did not mean the knowledge of stone was lost. It simply found a new home behind the high walls of medieval monasteries. These secluded communities became the unexpected guardians of classical engineering. With the collapse of large-scale state logistics, their approach to stone shifted fundamentally from imperial extraction to pious conservation. They became masters of spoliation, the deliberate reuse of materials. A fallen Roman column would become the foundation for a new chapel. A pagan altar was reshaped into a Christian baptismal font. This was not mere recycling, it was a profound symbolic act, transforming the physical legacy of a fallen empire into the bedrock of a new spiritual order. When they did quarry new stone, their needs were different. The goal was no longer a 100-ton obelisk, but the perfect, manageable ashlar block for a soaring Gothic vault or the delicate slab for a sculpted saint. Their quarries were often small, local affairs, serving a single abbey or cathedral project. The innovations here were in precision and detail, refining the chisel work needed for intricate ribbing and tracery. This monastic stewardship through centuries of change ensured that the flame of quarrying craft was never extinguished, patiently waiting for the day when human ambition would once again turn its gaze to the mountains. The quiet monastic quarries were about to be swept up by a storm of stone and light. A new architectural ambition was rising across Europe, one that reached not just for the heavens but for the very sky itself. This was the Gothic ascent, a revolution in height and illumination that began not at the building site but deep within the quarry. The vision for these soaring cathedrals demanded more than just stone. It required a new kind of stone, shaped with a precision never before seen on such a scale. Every flying buttress, every delicate rib in a vaulted ceiling, was a piece of a colossal three-dimensional puzzle. A single block cut even slightly wrong could compromise the entire intricate structure. How could quarry masters possibly guarantee that a stone extracted from a muddy pit miles away would lock perfectly into place hundreds of feet in the air, next to stones shaped by different hands? The answer was a system of templates. Master masons would create exact wooden patterns for every single unique block needed for the project. These templates were then sent to the quarries, where workers would trace their outlines directly onto the rock face before cutting. This was the birth of standardized, interchangeable parts, centuries before the Industrial Revolution. The quarry floor transformed into an open-air factory, where stone was not merely extracted but pre-manufactured. This unprecedented coordination between the distant quarry and the cathedral workshop turned the chaotic process of construction into a seamless, flowing assembly. It was this hidden organization, this quiet conversation of wood and stone, that directly enabled the vertiginous heights and the flood of ethereal light that still defines these spaces today. The quarry had become the silent, essential partner in a dialogue between earth and sky. For Michelangelo, a block of marble was not a blank slate but a prison. His task as a sculptor was not to build, but to liberate the form he believed was already trapped inside, waiting to be discovered. This philosophical shift brought the quarry master and the artist together in a single person. He did not merely send orders to the quarries of Carrara, he journeyed there himself, spending weeks wandering the vast, stark landscapes of white stone. He would run his hands over the raw cliffs, studying the veins and fissures, searching for that one perfect block that held the David or the Pieta within its crystalline structure. This was a profound return to the source, a Renaissance homecoming not just in style but in substance. The same quarries that had fed the Roman Empire's appetite for grandeur were now being reopened, their stones sought after for a new kind of humanistic expression. The techniques were a refined echo of the Roman past, iron tools and wooden wedges, but the purpose had transformed. The quarry was no longer just an industrial site for producing building blocks. It was the sacred origin point of individual genius. This intimate, almost spiritual connection between the creator and the raw material elevated the entire craft. Quarrying was no longer a mere service to architecture. It was the essential first step in the birth of art itself, a collaboration between human vision and the soul of the mountain. This artistic revival, however, was merely the prelude to an even greater disruption, one where the very muscle of man and beast would be replaced by the relentless power of steam and steel. The Renaissance artist's intimate dialogue with stone was shattered by a sudden, thunderous crack. The 17th century introduced a new and violent player to the quarry, gunpowder. This was not a tool of precision, but one of raw, explosive force. For the first time, quarrymen could bypass weeks of backbreaking labor with a single, earth-shaking blast. The method was deceptively simple. Workers would drill deep holes into the unyielding bedrock, pack them tightly with black powder, and ignite a fuse. In an instant, what had taken generations to learn about careful fracturing was replaced by pure, concussive power. The results were transformative, but they came at a profound cost. This new power was a double-edged sword. While it could liberate vast quantities of rock for projects demanding rubble and aggregate, like road building and fortifications, it was notoriously indiscriminate. The very force that broke the mountain also hid a secret weakness. The shock waves from the blast would travel deep into the stone, creating a spiderweb of microfractures invisible to the naked eye. A block that looked perfectly solid on the outside could be gravely compromised within, its structural integrity shattered. This made the stone utterly unreliable for the kind of fine, monolithic work that defined earlier eras. No one would risk using gunpowder-shattered stone for a soaring cathedral column or a delicate marble statue. The quest for speed had created a fundamental trade-off, sacrificing the possibility of perfection for the brute efficiency of volume. The age of the pristine monolith, extracted whole from the earth, seemed to be ending, replaced by an era of fractured rock and fractured legacy. Yet, this very problem of lost quality would soon spark a counter-revolution, one that sought to marry the power of industry with the precision of the ancients. Gunpowder's reign of brute force could not last forever. The fractured stone it produced was a problem that demanded a more intelligent solution, and the answer arrived not with a bang, but with a quiet revolution in thought. The Age of Reason brought the full force of scientific inquiry to the ancient quarry. Pioneering natural philosophers like James Hutton began to see the earth not as a static creation, but as a dynamic system with a deep and legible history. They walked the cliffs and outcrops, meticulously mapping the layers, studying the subtle angles where one stratum met another. This was more than academic curiosity. It was a new operating manual for the earth itself. For the first time, quarry masters could look at a rock face and understand what lay beneath. They learned to read the bedding planes, the natural lines of weakness where stone could be persuaded to separate with minimal effort. By understanding the geology, they could predict the quality of a deposit hundreds of feet down and plan their excavations to follow the stone's own logic. The quarry shifted from a place of tradition and guesswork to one of calculated prediction. Extraction became a precise science, minimizing waste and maximizing the yield of perfect, structurally sound blocks. This rational approach did not just make quarries more efficient, it laid the intellectual foundation for everything that was to come. The mountain's secrets were finally being decoded, and the next great leap in power was now inevitable. The rational understanding of geology paved the way for a new kind of power, one that did not rely on the strength of human arms. The 19th century brought the roar of the Industrial Revolution directly into the heart of the quarry. The most profound change arrived with the steam engine, a machine that breathed with the power of fire and water. Its first crucial task was one of reclamation. Steam-powered pumps worked tirelessly day and night to drain flooded quarry floors. For the first time, entire layers of pristine stone, submerged for millennia, were brought within reach, opening up vast new reserves for a rapidly expanding world. But steam's true might was in its ability to lift. Steam-powered cranes and derricks transformed the quarry floor into a theater of mechanical strength. Where once 1,000 workers would have strained with ropes and ramps, a single machine, hissing and groaning, could now hoist a 50-ton block as if it were a child's toy. This was more than just an increase in power, it was a complete redefinition of the possible. The scale of stone that could be moved was now limited only by the strength of the steel cable, not the collective muscle of a community. Perhaps the most elegant innovation of all was the channeling machine. This steam-powered apparatus drove a relentless series of chisels back and forth, cutting perfectly straight, vertical channels into the rock face. It automated the very process that had consumed countless lifetimes, the painstaking work of defining and detaching a block. With this machine, the quarry's output soared to levels the ancient Egyptians or Romans could never have conceived. This torrent of stone was the physical foundation of the Victorian city, its grand train stations, its imposing town halls, and its sprawling bridges. The mountain was now being fed into the engine of modern progress, and the pace of extraction had become a deafening roar. A perfect block of stone is a prisoner in its own quarry until it finds a way to travel. The thunderous power of steam-driven machines meant nothing if the fruits of that labor could not reach the architect's table. The 18th and 19th centuries answered this challenge with a parallel revolution, one that unfolded not in the rocky pits, but across the very landscape through the deliberate creation of water and iron roads. Canals became the first great liberators of stone. Engineers carved these serene, artificial rivers across the countryside, and a single horse pulling a barge could now transport a load that would have required dozens of wagons and teams of oxen on rough, rutted roads. This was logistics transformed into a gentle, flowing science. A quarry in Portland, for instance, could load its famous white limestone directly onto barges, sending it on a smooth, watery journey to London to rebuild a city after the Great Fire. But the true game-changer arrived on tracks of iron. The railway did not just move stone, it annexed the quarry directly to the city. Specialized, massively reinforced flatbed cars were designed for one purpose: to carry the monumental bones of the new industrial age. A block of Scottish granite could now be loaded at the quarry face and travel, uninterrupted, to be set as a curbstone in London or a pillar in Manchester. This was the final piece of the puzzle, the complete integration of extraction and delivery. The local stone of a region was no longer bound by geography. It became a global commodity, and the face of the modern city was built from 100 distant mountains. Across the Atlantic, a new nation was building its own legacy from the ground up. The sheer scale of the American landscape demanded a new kind of quarrying, one driven by industrial muscle and a profound desire for permanence. The young United States did not have ancient Roman ruins to repurpose. Its identity would be carved directly from the continent's bedrock. Immense operations in states like Vermont, Indiana, and Minnesota became the engines of this ambition. From their depths came the rugged granite for the towering piers of the Brooklyn Bridge and the elegant limestone for palatial homes like the Biltmore Estate. State capitals across the country rose from these pits, their gleaming facades a deliberate statement of stability and democratic power carved in stone. This was not the precision of Gothic templates or the philosophical liberation of a Renaissance sculpture. This was about volume, durability, and speed. American ingenuity leaned hard into raw power. The chattering wire saw, a cable fed with abrasive sand and water, sliced through granite with a relentless, slicing hum that replaced the rhythmic strike of the hammer. High-pressure steam drills bored into the unyielding rock with a percussive force that would have stunned a Roman engineer. The quarry itself transformed into a breathtaking industrial spectacle, with derricks and cranes moving mountains of stone like toys, feeding a nation's insatiable appetite for construction. This era demonstrates a powerful truth. The way a society extracts its stone is a direct reflection of its identity. The American quarry was not just a source of building material, it was a forge for national character, proving that a country's most enduring monuments begin long before the cornerstone is laid, in the raw, powerful heart of the mountain itself. The relentless power of the industrial quarry met its match in the pursuit of perfection. For all the might of steam and steel, the quest for a flawless cut, one that left the stone's crystalline structure untouched, remained the ultimate goal. The 20th century delivered that precision not with more force, but with the hardest substance known to nature, diamond. The diamond wire saw transformed extraction from a brutal struggle into a graceful, almost surgical procedure. Picture a continuous loop of flexible steel cable studded with small, diamond-coated beads. This wire is threaded around a massive granite block and set into motion by a powerful motor. As it runs, the diamonds do their silent work, abrading the stone with a continuous, humming action. The cut is astonishingly clean, only a few millimeters wide, and almost whisper-quiet compared to the thunderous percussion of the past. This narrow curve, as it is called, means dramatically less rock is turned into worthless dust. Where traditional methods might waste a third of the quarry's valuable stone, the diamond wire salvages nearly every inch. More importantly, because it applies steady, localized pressure instead of a violent shock wave, it leaves the stone completely undamaged. There are no hidden microfractures to compromise its strength. A block cut with a diamond wire is structurally superior and therefore far more valuable, whether it is destined for a grand civic monument or a sleek kitchen countertop. This elegant tool represents the perfect fusion of material science and mechanical engineering. It is the final, logical step in a millennia-long conversation, proving that the most advanced solution is often not the loudest, but the one that listens most carefully to the stone itself. A quiet hum of hydraulics has replaced the thunder of gunpowder and the rhythmic strike of the hammer. Today's quarries are landscapes of giants, where machines of staggering scale orchestrate the extraction of stone. Enormous hydraulic excavators, their booms reaching stories high, work alongside massive front-end loaders that can shift dozens of tons of rubble in a single, graceful scoop. But for all their brute strength, the true finesse lies in a far more focused tool, the hydraulic splitter. This device achieves something remarkable. It gives modern operators the precision of an ancient Egyptian craftsperson wielding a wooden wedge, but but amplified by the raw, controlled power of industrial fluid dynamics. Here is how it works. First, workers drill a perfectly aligned series of holes into the granite or marble face. Into each hole, they insert a slender, powerful hydraulic piston. When the system is pressurized, these pistons exert thousands of pounds of outward force against the walls of the borehole. The stone has no choice but to yield, fracturing with a clean, sharp crack exactly along the predetermined line. It is surgical stone splitting. This method delivers the clean, predictable break that quarry masters have sought for millennia, but without the hidden damage of blasting or the slow, grueling labor of channeling. The result is a perfect block, its structural integrity completely intact, ready to be plucked from the earth by the mechanical hand of an excavator. This combination of pinpoint accuracy and colossal strength allows for the safe and efficient handling of stone on a scale that would have been a pure fantasy to the builders of the pyramids or the Pantheon. The relentless drive for efficiency continues, now guided by the silent, immense pressure of hydraulics, a force that finally marries the mountain's patience with the urgency of modern time. A silent, invisible grid now overlays the modern quarry, a digital blueprint superimposed upon ancient stone. The latest chapter in this long story is written not with chisels but with lasers and satellites. Laser scanners mounted on tripods sweep across the quarry face, their beams capturing millions of data points in moments. This process builds a breathtakingly precise three-dimensional map, a virtual twin of the rock formation. Engineers can then explore this digital model from their desks, rotating it, slicing it, and calculating the absolute optimal way to dissect the mountain. They can plan the cuts to follow the natural grain of the stone and extract the maximum number of perfect blocks, reducing waste to a bare minimum. This digital foresight is then handed off to the machines themselves. Massive excavators and towering drills now move with an uncanny, preternatural grace. Guided by constant signals from global positioning satellites, their blades and bits operate with millimeter accuracy. The operator is no longer just a driver, but a supervisor of a robotic dance, ensuring the machine follows the precise path laid out in the digital plan. It is the complete elimination of guesswork. This technology minimizes the age-old problem of human error and maximizes the yield from every single, valuable stone deposit. We have journeyed from the stone pounder to the silicon chip, a transition that proves innovation in this most ancient of fields is far from over. The conversation with the earth continues, but now we are listening with digital ears. Mount Rushmore stands as a perfect inversion of the quarry's purpose. Here, the goal was not to extract blocks for assembly elsewhere, but to carve a mountain directly into a monument, removing everything that was not the precedent's. This was subtractive sculpture on a colossal scale, a process that turned the entire mountain into its own quarry. To achieve this, sculptor Gutzon Borglum and his team wielded the most potent tool of the industrial age, dynamite. They used it with a surprising degree of finesse, with specialized powder men called powdermen setting charges to remove vast, predetermined sections of granite. This was not random demolition, it was calculated deconstruction. After the blasts cleared away the bulk of the rock, the real artistry began. Workers suspended from bosun's chairs high on the cliff face would move in with jackhammers and hand tools. Their most ingenious technique was a process called honeycombing. They would drill a dense grid of closely spaced holes, sometimes just a few inches apart. This perforated the granite, creating a web of weaknesses. Then, using hammers and chisels, they could carefully knock out the thin webs of stone left between the holes. It was a method of convincing the mountain to release its surface in controlled, manageable pieces, a direct echo of the ancient practice of using channels and wedges, but scaled up to the size of a national landmark. This project represents a unique fusion of eras, where the raw, explosive power of industry was meticulously guided by the patient, detailed hand of the artist, proving that even in the 20th century, the fundamental conversation between human intention and stone remained exactly the same. The relentless hum of modern extraction is now accompanied by a new, quieter imperative, the need for stewardship. The same industry that has shaped our world for millennia is learning to heal the land as it works. Advanced water recycling systems have become commonplace, ensuring that the vast quantities needed to control dust and cool diamond-tipped saws are cleaned and reused in a continuous, closed loop. This not only preserves a precious local resource but prevents any contaminated runoff from affecting the surrounding ecosystem. Dust, once the visible signature of a working quarry, is now meticulously managed through automated misting cannons that envelop the site in a fine, settling spray. But the most profound shift happens after the last block is hauled away. An exhausted quarry pit is no longer seen as a scar but as a blank canvas for renewal. These vast, open spaces are being reborn as vibrant wetlands that attract native bird life, transformed into serene recreational lakes for communities, or carefully prepared for sustainable housing. The entire process, from the diesel fuel in the excavators to the long-haul transport of finished stone, is now under scrutiny with a clear drive to minimize the carbon footprint at every stage. This evolution demonstrates that the ancient story of quarrying is not ending, it is simply entering its most conscious chapter. The legacy of our monuments is no longer just in the stone we erect, but in the living, breathing landscape we choose to leave behind. That deep, tactile knowledge of stone was not learned in a classroom, but carved into the very hands of the workers themselves. For every engineering marvel we have explored, from the pyramids to the Parthenon, there stands an invisible army of individuals whose lives were intertwined with the dust and the din of the quarry. In ancient Egypt, the workforce was a complex mix of conscripted laborers fulfilling a civic duty and highly skilled artisans who commanded respect. These seasoned crafters could read the limestone or granite face like a map, spotting a hidden fissure by a subtle change in color or tone, knowing precisely where to place their wedges for a clean break. This was an expertise born of a lifetime of observation, a wisdom passed from father to son, from master to apprentice, through the direct language of demonstration and touch. Their labor was the foundation upon which all innovation was built. Moving forward through time, the great cathedrals of Europe rose on the shoulders of guilds of masons, men who guarded their stoneworking secrets as closely as any trade guild. And in the booming quarries of 19th century America, it was often newly arrived immigrant communities from Ireland, Italy, and later parts of Eastern Europe who provided the immense physical effort. They brought their own traditions of extraction and carving, blending old-world techniques with the raw, industrial demands of a new nation. Their work was marked by hardship and very real physical risk, from falling stone to the slow, lung-chilling toll of silicosis, an illness caused by years of breathing in fine rock dust. To walk through a cemetery near an old quarry is to see this history written in stone, with markers bearing names from across the globe. This human legacy reminds us that the true monument is not just the finished obelisk or the grand facade. It is the collective story of resilience, of shared knowledge, and of the unnamed thousands who, block by block, literally built the world we walk through today. The choice of stone was never just about beauty or proximity. It was a deep, practical calculation of a material's very soul. Why did the pyramid builders commit to the soft, golden limestone of Tura, while the architects of the Parthenon insisted on the radiant marble of Mount Pentelicus? The answer lies not in ledgers, but in the fundamental properties of the rock itself, a science ancient cultures understood through generations of hands-on experience. Limestone is a sedimentary rock formed from the compressed remains of ancient sea life. This gives it a relatively soft, uniform consistency, making it surprisingly workable with copper tools and stone pounders. For the Egyptians, who needed to shape and move over 2 million blocks with breathtaking speed, this workability was everything. It was the perfect balance of durability and ease, a material that could be quarried in colossal quantities and then precisely dressed to create those iconic, seamless slopes. Marble, on the other hand, is limestone transformed by immense heat and pressure deep within the earth. This metamorphic process recrystallizes the stone, giving it a tighter, interlocking grain. The result is a material with remarkable tensile strength. It can withstand significant bending forces without snapping, a property absolutely essential for the Parthenon's elegant, fluted columns and the long, unsupported lintels of its entablature. Furthermore, marble possesses a translucency that limestone lacks. Light penetrates its surface just enough to give it a soft, internal glow, making the sculpted gods and heroes on the frieze seem almost alive in the Athenian sun. It was the only choice for a temple designed to celebrate divine perfection and human reason. Then there is granite, the unyielding titan, formed from molten magma that cooled slowly underground. Its interlocking crystals of quartz and feldspar make it brutally hard, resistant to both weathering and abrasion. The ancients reserved this formidable material for statements of absolute permanence. In Egypt, it was used for the sarcophagi meant to last for eternity, and the towering obelisks that pierced the sky as symbols of pharaonic power. For the Romans, it was the foundation stone of empires, ideal for paving heavily trafficked forums and building enduring aqueducts. This intuitive grasp of material science was the quarry master's first and most critical blueprint. Before a single wedge was hammered or a channel was cut, the rock itself had already dictated the methods, the tools, and ultimately, the legacy of the monument it would become. The shadow of the mountain stretches long, and not every stone cut from the earth was destined for glory. For every triumphant pyramid or cathedral, history holds the blueprints for projects of staggering ambition that were ultimately abandoned, their stories etched not in polished facades but in the raw, fractured surfaces of the quarries themselves. These silent failures are, in their own way, as profound as the successes. They reveal the absolute outer limits of an era's technology and logistics, a stark line drawn by the immutable laws of physics. Consider the Baalbek monolith in Lebanon, a companion piece to the unfinished obelisk in its sobering lesson. This colossal block of limestone, quarried by Roman engineers, weighs an estimated 1,650 tons. It is a breathtaking sight, a perfectly shaped stone that was successfully detached from the living bedrock, yet there it remains, resting in its quarry for nearly 2,000 years. It was never moved an inch. The sheer scale of the monolith defeated even the Romans, masters of logistics who had built stone railroads and harnessed the power of pulleys. To move a block of that mass would have required a coordinated effort of thousands of workers, an immense system of ropes and rollers, and a perfectly engineered road, all for a single, unimaginably risky journey. The fact that it was cut free proves their ambition, but its eternal stillness reveals their limit. These projects are humbling monuments to human aspiration. They teach us that the path of monumental construction has always been paved with both triumph and overreach, and that sometimes the most valuable lesson a mountain can offer is a quiet, unyielding no. A Roman quarry master in Britain might have recognized the familiar rhythm of the iron chisel, but the stone itself would have been a stranger. The flow of quarrying knowledge was never a one-way street. It moved along the arteries of empire and trade, a silent passenger on ships carrying spices and soldiers. As legions marched, they brought with them the standardized Roman blueprint for extraction, the precise channeling, the use of iron tools, and their ingenious rutways for transport. These methods were imposed upon the landscapes of Gaul, Iberia, and North Africa, reshaping local traditions to feed the empire's endless appetite for stone. Centuries later, the currents of exchange reversed. European colonizers, armed with gunpowder and a new industrial confidence, carried their own quarrying doctrines to the Americas and Asia. They encountered landscapes of stone utterly unlike their own, and their rigid methods often faltered. In response, a quiet, practical adaptation began. Spanish builders in Mesoamerica, for instance, observed how indigenous masons worked with local volcanic rock, a material far more brittle than European limestone. They began to integrate these insights, blending old-world ambition with new-world material wisdom. This was not just conquest, but a genuine, if unspoken, collaboration. The cross-pollination even extended to simple tools. The design of a wooden wedge in an Indian quarry might slowly evolve after contact with a Dutch trader's iron version. A technique for floating stone barges down a Chinese river could inspire a new solution for a French canal project. This global tapestry, woven from countless such threads of shared and adapted knowledge, proves a profound truth. The greatest innovations in human history were rarely born in isolation. They emerged at the crossroads where different ways of understanding the earth met, clashed, and ultimately created something entirely new. The ancient rhythm of hammer on chisel is being replaced by the near-silent whir of drones and the quiet calculations of artificial intelligence. This is the emerging frontier of the fully automated quarry, a place where human hands may never touch the stone until it is already a finished product. Unmanned aerial vehicles now float above the vast excavation sites, their high-resolution cameras and LiDAR sensors building live, three-dimensional maps of the quarry face with centimeter accuracy. These digital twins are so precise they can reveal the subtlest hairline fractures within a block of granite, allowing engineers to approve its extraction or reject it before a single machine is deployed. This predictive power is revolutionizing the entire process, minimizing waste and guaranteeing quality from the very beginning. On the ground, the transformation is just as profound. Autonomous haul trucks, guided by a web of GPS and onboard sensors, now navigate the treacherous quarry roads in a perfectly synchronized, continuous ballet. They operate around the clock, untroubled by fatigue or hazardous dust, moving mountains of material with relentless, safe efficiency. The logical endpoint of this technological arc is staggering to consider. Could we one day see robotic arms, programmed with the design for a monumental arch or a complex sculpture, begin the carving process right at the quarry wall? The raw block would be shaped at its source, its journey to the construction site already a final step. This digital evolution does not erase the ancient relationship between human ambition and stone. It simply redefines the craftsman's role. The quarry worker becomes a data analyst, a systems supervisor, a conductor of a silent, automated orchestra. We are witnessing the birth of a new kind of precision, one that promises to extract our future monuments with an intelligence the pyramid builders could scarcely have dreamed of, all while treading more lightly on the earth they revered. From the fire-hardened sticks of prehistory to the GPS-guided excavators of today, the story of quarrying is a relentless narrative of human innovation. Every architectural wonder we have ever admired rests upon this hidden foundation of extraction. The Great Pyramid's smooth slopes were born from the simple genius of swelling wooden wedges. The Parthenon's radiant columns owe their existence to the iron chisel and the revolutionary power of the lever. The soaring Gothic cathedral was pre-assembled in its quarry, guided by wooden templates. The industrial cityscape was carved out by the thunderous force of steam, and the flawless surfaces of our modern monuments are cut with the silent, surgical precision of diamond. Each leap in our ability to pull stone from the earth directly enabled a new leap in what we could build. These quarries are the unsung birthplaces of civilization's most iconic landmarks. They remind us that a monument is not merely an object of admiration, but the final chapter in a much older, more dramatic story of ingenuity and sheer will. The next time you find yourself standing before an ancient pyramid or tracing the lines of a marble statue, remember the quarry it came from. Consider the centuries of accumulated knowledge, the generations of craft, and the quiet, relentless problem-solving that made its existence possible. This journey through stone is a testament to our enduring drive to shape the world. If this exploration has captivated you, we would love to hear which quarrying innovation you find most impressive. Share your thoughts in the comments below and subscribe for more deep dives into the hidden stories that built our world.